Good day. So my name is Padilla John Michaal Gabrielei, and I am with my partner Bordonada Gaille. So we are here to discuss the topic of noise and its effect in communication. So first, we must define what is noise. So noise can be simply defined as unwanted signal that interferes with the original message. So as much as possible, we should try to eliminate noise because not only does it interfere with the original signal, but it somehow alters the message we are trying to send, which gives the receiver an unclear version of the original message. So, noise in communication can be divided into two types. So, those two types are external noise and internal noise. So under those two types of noises, we have specific types. So under external noise, we have atmospheric noise, extraterrestrial noise, and man-made noise. On the other hand, in internal noise, we have thermal noise, shot noise, and transit time noise. So under external noise, first we have atmospheric noise. So atmospheric noise is caused by lightning discharges found in thunderstorms, and it can also be found in other natural electrical disturbances. So those disturbances also cause noise in signals that we are trying to send. So next up is extraterrestrial noise. So extraterrestrial noise can be divided into two groups, namely solar and cosmic. So for the first one, under extraterrestrial noise, which is solar, so solar noise is an electrical noise that comes from the sun, from the moon itself, which is solar. So the sun, it constantly radiates energy which affects a wide frequency spectrum, and the frequency spectrum that it affects is mainly the spectrum used for radio communication. So the sun also has an 11-year noise cycle in which at the peak of the cycle it releases or produces a large amount of noise that causes interference to the radio signals we are trying to send and process. So the second noise under extraterrestrial noise is cosmic noise. So cosmic noise can be simply defined as the electrical noise that comes from distant stars, and it also comes from the galaxies around us, and it is commonly known as thermal noise. So what's unique about this noise is that it's uniformly distributed in our atmosphere. And lastly, for external noise, another type is man-made noise. So man-made noise, it can also be called as industrial noise. So this kind of noise is basically the noise that comes from heavy electrical machines that we use in the industry, and those machines are producing quite amount of noise when they are operating. So we are now going to move on to the second type of noise, which is internal noise. And under internal noise, we have thermal noise. So what is thermal noise? Thermal noise is also known as Johnson noise. So this noise is commonly generated due to the movement of charge carriers, and that movement is known as thermal agitation. So next up under internal noise is a noise that is commonly seen in some circuits. So this type of noise is shot noise. So shot noise is a type of internal noise that is said to be dependent in the current flow all throughout the system. So it depends on the what we call distinct nature of charges. So next up under internal noise is transit time noise. So this type of noise commonly occurs in high frequencies. So first let's define the term transit time. Okay, so transit time can be defined as the amount of time needed for charge carriers to travel to another side, like for example electrons to holes. So at high frequencies, those carriers are not able to travel to the other side even though the distance between those two regions are just small. They're still not able to travel to the other side in high frequencies, and their inability to travel to the other side is visualized as a noise. So the inability to travel to the other side, that is what causes transit time noise. So next up in internal noise is miscellaneous. So in miscellaneous noise, we can divide it into three. So for the first part is flicker noise. So it's also known as 1 over F noise. So this type of noise is commonly found in carbon composition resistors, and it is also commonly detected with thermal noise. And next is transistor noise. So from the name itself, transistor noise is the type of noise that is produced by the internal resistances of the transistor's terminals. So those terminals are the base, emitter, and the collector of a transistor. So lastly, which is partition noise. So partition noise is the type of noise that occurs when a current flowing through the system is being divided. So as the current is being divided, fluctuations in the current levels also occur. So those fluctuations during the division of current is what causes partition noise.
So next we have is the noise computation, wherein you can use these formulas to compute for different aspects that is related to noise. So first we have is the noise power. Noise power is the measured total noise in a given bandwidth at the input or output of a device when the signal is not present. So to compute for the noise power, you can multiply the Boltzmann constant of 1.38 times 10 raised to negative 23 and then multiply to the absolute temperature of the device. Please remember that this is in kelvins, and the circuit bandwidth. Next we have is the signal to noise ratio. The signal to noise ratio is computed by the average signal power divided by the average noise power. You may also compute for this by 10 times log base 10 signal power over noise power. Please take note that this formula is used to get the answer in decibels. Next we have is the noise figure. The noise figure represents the degradation in signal to noise ratio as the signal passes through a device. It is usually represented in decibels. To compute for the noise figure, you can multiply 10 to log base 10 to the noise factor, which is represented by F. And you can also compute for the noise figure by subtracting the output signal to noise ratio from the input signal to noise ratio. Please do remember that the signal to noise ratio should be in decibels. After that, we have the noise factor, which as I said earlier is represented by F. This is equal to the quotient of the signal to noise ratio of the input over the signal to noise ratio of the output. Please do take note that the noise factor is always greater than 1. Next we have is the noise density. The noise density is also known as the power spectrum density. It is a figure that determines the amount of noise contained in a specified bandwidth. Simply put, this is the average noise power per hertz of bandwidth. So to compute for the noise density, you can divide the noise power over the bandwidth, and it can also be equal to the Boltzmann constant to the temperature of the device. Next we have is the noise current. So the noise current may be computed using the square root of 4 times conductance times the Boltzmann constant times the temperature and times the bandwidth. This is in amps, obviously. Next is the noise voltage. The noise voltage may be computed by, again, the square root of 4 times the Boltzmann constant times temperature times bandwidth times the resistance. This is in volts. Here we have another formula for the noise voltage. This is for the total RMS noise voltage. In order to get this value, you only need to square root the sum values of the different noise voltages of the different resistors, and you have to square them each first. After that, we have the noise temperature. So noise temperature is obviously related to thermal noise, as discussed earlier. Since most input noise comes from thermal noise, noise temperature is used as a common basis for measuring random electrical noise from any source. To calculate for the noise temperature, you only need to multiply the reference temperature, which is 290 Kelvin, to the difference of the noise factor, -1. Lastly, we have the shop noise. To calculate for the shop noise, you only need to multiply 2 to the sum of the direct current and the reverse saturation current. Then we multiply that to the charge, which is equal to 1.602 times 10 raised to -19, and the bandwidth. And that's all for the noise computation.